In particle physics, a hadron ℏ is a composite particle made of quarks held together by the strong force. Hadrons are categorized into two families: baryons, made of 3 quarks, and mesons, made of 1 quark and 1 antiquark. Protons and neutrons are examples of baryons. Pions are an example of a meson. Hadrons containing more than 3 valence quarks have been discovered in recent years. A tetraquark state, named the Z-, was discovered in 2007 by the Bell collaboration and confirmed as a resonance in 2014 by the LHCb collaboration. 2 pentaquark states, named P+C and P+C, were discovered in 2015 by the LHCb collaboration. There are several more exotic hadron candidates, and other color singlet quark combinations may also exist. Of the hadrons, protons are stable, and neutrons bound within atomic nuclei are stable. Other hadrons are unstable under ordinary conditions. Free neutrons decay with a half-life of about 611 seconds. Experimentally, hadron physics is studied by colliding protons or nuclei of heavy elements such as lead, in detecting the debris in the produced particle showers. Etymology: the term hadron was introduced by Lev B. Okun in a plenary talk at the 1962 International Conference on High-Energy Physics. In this talk he said, "Notwithstanding the fact that this report deals with weak interactions, we shall frequently have to speak of strongly interacting particles. These particles pose not only numerous scientific problems, but also a terminological problem. The point is that strongly interacting particles is a very clumsy term which does not yield itself to the formation of an adjective. For this reason, to take but one instance, decays into strongly interacting particles are called non-leptonic. This definition is not exact because non-leptonic may also signify photonic. In this report I shall call strongly interacting particles hadrons, and the corresponding decays ḥædronic. I hope that this terminology will prove to be convenient." Lev B. Okun, 1962. Properties. According to the quark model, the properties of hadrons are primarily determined by their so-called valence quarks. For example, a proton is composed of 2 up quarks and 1 down quark. Adding these together yields the proton charge of +1. Although quarks also carry color charge, hadrons must have 0 total color charge because of a phenomenon called color confinement. That is, hadrons must be colorless, or white. These are the simplest of the 2 ways. 3 quarks of different colors, or a quark of 1 color and an antiquark carrying the corresponding anticolor. Hadrons with the first arrangement are called baryons, and those with the second arrangement are mesons. Hadrons, however, are not composed of just 3 or 2 quarks, because of the strength of the strong force. More accurately, strong force gluons have enough energy to have resonances composed of massive quarks. Thus, virtual quarks and antiquarks, in a 1-to-1 ratio, form the majority of massive particles inside a hadron. The 2 or 3 quarks are the excess of quarks versus antiquarks in hadrons, and vice versa in antihadrons. Because the virtual quarks are not stable wave packets, but irregular and transient phenomena, it is not meaningful to ask which quark is real and which virtual, only the excess is apparent from the outside. Massless virtual gluons compose the numerical majority of particles inside hadrons. Like all subatomic particles, hadrons are assigned quantum numbers corresponding to the representations of the Poincare group, JPC, where J is the spin quantum number, P the intrinsic parity, and C, the charge conjugation, and the particle's mass. Note that the mass of a hadron has very little to do with the mass of its valence quarks, rather, due to mass-energy equivalence. Most of the mass comes from the large amount of energy associated with the strong interaction. Hadrons may also carry flavor quantum numbers such as isospin and strangeness. All quarks carry an additive, conserved quantum number called a baryon number, which is plus 1/3 for quarks and minus 1/3 for antiquarks. This means that baryons have B equals 1 whereas mesons have B equals 0. Hadrons have excited states known as resonances. Each ground state hadron may have several excited states. Several hundreds of resonances have been observed in particle physics experiments. Resonances decay extremely quickly via the strong nuclear force. In other phases of matter the hadrons may disappear, for example, at very high temperature and high pressure, unless there are sufficiently many flavors of quarks. The theory of quantum chromodynamics predicts that quarks and gluons will no longer be confined within hadrons, because the strength of the strong interaction diminishes with energy. This property, which is known as asymptotic freedom, has been experimentally confirmed in the energy range between 1 GeV and 1 TeV. All free hadrons except the proton are unstable. Baryons. All known baryons are made of 3-valence quarks, so they are fermions, i.e., they have odd half-integer spin, because they have an odd number of quarks. As quarks possess baryon number B equals 1/3, baryons have baryon number B equals 1. The best known baryons are the proton and the neutron. One can hypothesize baryons with further quark-antiquark pairs in addition to their 3 quarks. Hypothetical baryons with one extra quark-antiquark pair are called pentaquarks. As of August 2015, there are 2 known pentaquarks, P plus C and P plus C, both discovered in 2015 by the LHCb collaboration. Each type of baryon has a corresponding antiparticle in which quarks are replaced by their corresponding antiquarks. For example, just as a proton is made of 2 up quarks and 1 down quark, its corresponding antiparticle, the antiproton, is made of 2 up antiquarks and 1 down antiquark. Mesons. Mesons are hadrons composed of a quark-antiquark pair. They are bosons, meaning they have integral spin, i.e., 0, 1, or -1, as they have an even number of quarks. They have baryon number B equals 0. Examples of mesons commonly produced in particle physics experiments include pions and kaons. Pions also play a role in holding atomic nuclei together via the residual strong force. In principle, mesons with more than one quark-antiquark pair may exist. A hypothetical meson with 2 pairs is called a tetraquark. Several tetraquark candidates were found in the 2000s, but their status is under debate. Several other hypothetical, exotic mesons lie outside the quark model of classification. These include glue balls and hybrid mesons.